Hello, we are Group 34 and our project is the development and optimization of a basic Industry 4.0 framework for composites manufacturing. So, Industry 4.0 refers to using modern technology like AI, IoT devices, and cloud computing for industrial processes. An Industry 4.0 framework for composites manufacturing would then be a workflow for adapting older processes to work with these modern technologies. For our project, we looked at the composite manufacturing process of curing. Curing occurs when a material undergoes chemical changes at a certain temperature to strengthen the material. This process occurs in a curing oven, and because a material's internal temperature is not measurable, the process runs much longer than necessary. Our project uses machine learning and IoT sensors to determine when this internal temperature point is reached.
To do this, we collected a dataset of the internal and external temperatures of an aluminum cylinder undergoing curing. We used an array of temperature sensors to accomplish this. The interior temperature was obtained by boring a small hole in the cylinder and inserting a sensor inside. Using the external temperatures, our goal was to create a machine learning model to guess the interior temperature and therefore predict when the curing process was finished. While we were confident with the data we had, it was not feasible to test for all permutations of an object in a heating chamber. To account for this, we designed a simulation of a heat chamber in MATLAB. This allowed us to account for different geometries, materials, and configurations within the heat chamber that would have been otherwise infeasible. Later iterations of the process tried to simulate the PID control system within the heat chamber. After we had obtained our data, we needed to determine what machine learning models would be most effective for our dataset. To accomplish this, we started with pre-existing machine learning libraries and identified the models that worked best for our purposes. We settled on models with proven results in predicting time series data, random forests, and short long-term memory, or LSTM, neural networks.
Random forests are a set of forking decision paths that lead to unique outputs. By weighting decisions using the training dataset, the model will predict the interior temperature. The advantage of this model is its speed and its ability to perform well with little data. In the case of LSTMs, the model uses recurrent networks which form a graph along a temporal sequence using the internal state to form a time-based memory. The utility of this model is it's tailored for time series data. Machine learning requires a dataset in two parts, input data and training data. The model takes the training data and by continuously pitting the neural network output against the true output, a general set of coefficients are produced which will in theory produce accurate outputs given new inputs, therefore learning the data. In both cases, the refining of accuracy of the predictions was a lengthy process. While this largely involved tweaking the parameters, scaling, preprocessing, and filtering the data was also useful. Filtering was done using Kalman filters which reduced the noise caused by the analog to digital converters.
For both the random forest and LSTM neural network, the models accurately produced the interior temperature given the external temperature. As seen on the diagram, while both were below 7% air, the LSTM model would accurately predict a soak time within 1% of the actual soak time. In this regard, we have successfully implemented Industry 4.0 to solve a problem in composites manufacturing, and overall, the final design is an effective proof of concept for demonstrating the feasibility of the system for composites manufacturing.
While we feel that we accomplished what we set out to do in this project, due to COVID-19 we lost access to the lab earlier than expected. If we had the full year to work, we would have tried to fully integrate machine learning into the heat chamber's control system to make predictions in real time. This would then terminate the heating process after reaching the goal temperature and soak time. While the code exists, due to the closure in the lab, this was never implemented. Another area of research would be to validate the heat chamber simulation. With more datasets, we could fine-tune and validate the simulation, which would greatly expand the utility of our machine learning model. However, the most useful application of this process is the framework itself. Although our project is focused on a specific process, the principles of Industry 4.0 create a basic framework for other uses in composites manufacturing. Following the framework of our project, we created a basic procedure to implement this in other composite manufacturing processes. We are excited to see what processes will make use of this powerful tool next.